Okay, I put this slides at the last one of that session just to explain how the ground can influence the capacitance of a transmission line, because we have two types of transmission line, overhead lines and underground cables. I mentioned at the beginning of this session, the underground cable usually may have more capacitance than overhead line. So even they are made by the same material, because the underground cable is closer to ground, even the end of the ground, touching the ground. So it doesn't mean it has short circuit to the ground. It just isolated by the outside skin insulation. But because it's very close to the ground, that will increase capacitance of the transmission line. Why? Because the capacitance depend on the electric field. Remember how we calculate the capacitance? We first assume each conductor carries certain charge Q, and that will make a electric field. And based on the density of the electric flux, and we calculate the potential or the work you need to do to carry a unit charge from one point to another point. So usually we want to calculate the charge moving from the conductor to maybe not a certain distance. That could be another conductor. So if the ground is far away from the conductors, so electric field will be perfectly symmetric. So that makes calculation easier. But if the ground is close to the conductor, you see that the electric field will be distorted. So it will be you see the direction of flux will change. Finally, will near the ground. So that makes calculation harder. But we can have a method to simplify the calculation. So the method, let me make sure. Yes. Okay, so the method is called image charge method. The image charge method means instead of considering just single conductor in this more complex electric field, maybe we just add another conductor as the image of this conductor. So we can get rid of the ground surface, and we add another conductor with exactly same value of charge, but the negative sign. Okay, because when you put the two, the Q and the negative Q in the space, so on their middle surface, that will have zero potential, which is equivalent to having the ground surface there, right? Because the ground will always have zero potential. When you put two Q and a negative Q in the middle, that surface, that plane, that will be zero. That will have zero potential. So it's the same as calculating the capacitance for this case. All right, so what if we have a single phase transmission line, which means we'll have one conductor carrying charge, we call it the QA. We have another conductor carrying charge, negative QA, because they need to send the current back. So the two conductors together will have a closed system with zero net charge. And on the other side of the ground surface, we need to put two fictitious conductors. So this one will be image of the first one. So that will be a negative charge. Let me try. I use different color. So the first one is QA. The second one, so this is a negative QA. So that's the image of the first conductor. And the other conductor also need to carry negative charge. So this one is also a negative QA. And the last one will be just QA. Okay, so the two right one carry the positive charge. The two blue one will carry negative charge. And based on the geometry, you can know. So this distance is double head. So if you measure how high the conductor from the ground. So this length, this side will be a 2H. And diagonal, we call it just H12. So there's a triangle. Based on this triangle, if we know the distance D, based on this triangle, we will be able to calculate the H12 by diagonal theorem. Okay. So now you understand if the H is infinite, far away from the ground, 2H and H12 will be very close. So which means electric field is not changed by the ground or by the middle surface. So on the textbook, there's a homework problem, but I only gave it at homework problem because I can just quickly demonstrate how to solve it. It's not very hard. But the problem asks you to prove if we consider the ground, the capacitance per a conductor will satisfy this formula. So you see, this formula is very similar to the formula we know if this part is 1, right? So our original formula to calculate capacitance per conductor will be 2 pi epsilon 0 divided by log. Then there's a fraction d, capital D by lowercase r. But here, because we have the ground, so you need to consider this factor. This factor is the numerator is the length of one edge of the triangle, and the denominator is the diagonal of the triangle. Okay, so they are not equal when the conductor is close to the ground. So we need to consider the triangle. So how to prove this formula? So before we prove it, let's just, if H go to infinite, okay, this factor will be 1, okay. But if H is become smaller, 2H divided by H12 will be smaller. So which means capacitance will increase. So H smaller, 2H divided by H12. So this one is actually cosine theta, right? If this is the cosine theta. So this one will become smaller. If this one becomes smaller, C will increase. So that's a reasoning behind the observation about the increase of capacitance of an underground cable. So we get closer to the ground, the capacitance will increase. You color them. Okay. So how to prove this one? So there are 2 methods we can use. So first, we can start from the definition of capacitance. We will study when we move a unit charge in this electric field formed together by 4 conductors, 2 actual conductors and 2 fictitious conductors. So when we move a single unit charge from one place to another place, we try to find that formula, and that work can help you to calculate the voltage change. And the voltage change, and also we know the volume of charge, we'll be able to calculate capacitance. So now we'll consider there's a 4 electric field, right, instead of single one. And each electric field will determine by different charge. If the first one is QA, the next one is negative QA, and the third one is QA. The fourth one, the last one is negative QA. This is just basically the same idea as the original one we proved, the capacitance between 2 conductors. So if you simplify this formula, that will give you the final answer. Okay, same, you almost get there. So then by the definition, capacitance between A and B, so this is capacitance between 2 conductors, that will be this formula. Okay. And next one, we want to just consider capacitance of a single conductor to the middle point. That will be equal to 2 times of the capacitance between two conductors. So this is the final answer. That's from the definition of capacitance. The method 2 is much simpler. Method 2 will utilize the the idea of calculating GMD and GMR. Once we know the GMD and GMR, we'll be able to just calculate the capacitance by just by the formula. So the formula is C is equal to 2 pi epsilon 0, then log, then there's a GMD divided by GMR. GMR is GMRC, right? So if we know the GMD and GMR, we'll be able to calculate capacitance directly from that formula. Then the question will be, how do we determine GMD and GMR? GMD is defined as the distance between two groups. And GMR is defined to be the average distance within each group. Okay, so the grouping will be the key here. So how do we define the groups among those full conductor? We need to, we just follow the color here, right? So we have red group, which carry the same charge, and we have a blue group also carry the same charge. So if the red group carry the positive charge and the blue group carry the negative charge. So to calculate the GMD will be the distance between the red group and the blue group. Let me clean up a little bit. So to calculate GMD, if we start from any single conductor, let's from the first one. So it will have distance here, which is D. And they will have another distance to blue group, that's a 2H. Okay. Similarly, you can move to the next one, so it will have a D and 2H. So finally, we need to calculate we need to consider all combination. So we have 2D, we have the product of the 2Ds, and we also have a product of 2Hs. Then we calculate average. So this is a GMD. The GMR is the mean distance within each group. For instance, if we choose the red group, to choose red group, we have the radius on its own, and we have the distance, which is 2H, H12, right? So then we move to the next conductor, we'll have the product of 2 Rs and the product of 2 H12, 2 diagonals. So they will be GMRC. Okay, so next one, the capacitance for each group, we directly apply this formula. We'll get this one. But if you compare this one to the final answer, the only difference is there's a factor 4 and this factor 2. So which means if we use that formula, we'll calculate the capacitance for each group, which is twice of the answer. Why? Because this is capacitance for each group. And we want to know the capacitance for each conductor. So we need to divide this one by 2. Okay, so we can consider the capacitance between the two groups as like parallel connections of conductor to conductor. So we have to divide this answer by 2. So then there will be the final answer. Okay, so either method can give you the correct answer. Yeah, we don't have to remember this formula. Just give you an example showing how the capacitance can increase when the distance to the ground becomes shorter. So I mentioned one project I did I guess 15 or 16 years ago for Long Island. Long Island, they have a local power company called Long Island Power Authority. So we did the system restoration study. We will help them to evaluate their black star plan. Black star means if the system is in completely power outage or blackout, and they need to have some unit they can start first. Usually such unit will be gas turbine or combined cycle combustion turbines, which can start in like 10 minutes or 20 minutes. And then they use this unit to energize first some transmission line, then pick up some load. So when they connect transmission line to energize the transmission line, because they cannot add load to the line. So they will connect to a line with no load. For such cases, the far end will create a very high voltage because most of lines are underground, so they have a capacitance. So you can imagine when you connect a line, the line is connected to a capacitor. So the line may have overvoltage problem. So such a restoration plan is very different for a system with all overhead line. With overhead line, if you energize a long transmission line, it may cause, when you increase the load, it may cause a low voltage problem. But for Long Island system, the overvoltage problem can be a problem, can be the main concern. All right, so let's move to a next section. Okay, line model and performance. So this section will utilize some the formulas we learn about calculating the inductance, capacitance, and the resistance. In this session, we'll focus on discussing the calculation for 3 types of lines, from a short line, medium lines, and long lines. So we'll introduce different line models. So which model to choose usually depend on the lines of line. Usually we can, typically we can use some threshold if the line is shorter than 80 kilometer or 15 miles. Usually such voltage is at 69 kV or lower. We can take a short line model. So short line model is pretty simple, it's just impedance. So basically if we study any system with all devices connected by short lines, it's similar to a calculation for in section 203, just for conventional AC circuit. But when we move to a medium line or long line, so each line cannot be represented by single impedance. We'll explain why. For medium line, so that will be the in the range from 80 kilometer to 250 miles, 250 kilometer. Which is about 50 miles to 150 miles. For medium line model, we can use a lump line parameter, which means if we need to consider resistance, impedance, reactance, or shunt admittance to the ground, you can just consider, you can treat those parameters together as just a single element connected to somewhere to the line. The location is not really, doesn't really matter. But once you move to a long line model, longer than 250 kilometer, it's not accurate anymore, just treat the total resistance, for example, of the entire line only stay at one phase of line. You have to split into many small pieces, distribute the parameter along the transmission line. So that will make calculation more challenging. Okay, we'll use one example from the previous section to talk about why we have such a boundaries, 80 kilometer and 250 kilometer. This is the same example we discussed before. So it's all aluminum conductor with GMD 35 inch. And GMR C 1.3, GMR L 1.0 inch, and we know the role. And if we assume operate the line in 60 Hertz system, so we're ready to calculate the total resistance, total reactance of the line. Okay. So from the formulas we proved from a previous section, we just need to plug in the GMD, GMR into the formula to calculate L and C. And we use a lowercase r to define the resistance per kilometer. And L in this section will be the inductance per kilometer in the unit of millihenry per kilometer. And the C will be the capacitance per unit length with unit mu F per kilometer. So we put this table. Let's do the calculation for the two boundary value. 80 kilometers separating the short line from a medium line, and 250 kilometers separating from a medium line to long line. Okay, so let's just plug in the value of L, the length of line, into those formula to see what the total resistance or readiness. For readiness, we consider both inductive readiness and capacitive readiness. So inductive readiness is connected in series with the resistance. Capacitive readiness actually means the readiness to the ground. It's the readiness between the conductor to the ground. So the smaller the R and XL, which is in the series connection in the conductor, the smaller those value, which means the more likely we can ignore those parameters. For the capacitive readiness, it is the readiness between the conductor to the ground. If this value is very small, we cannot ignore this capacitor. Okay. So let's just do the calculation. So R for 80 kilometers, that's about 0.6 ohm. For 250 kilometers, about 2 ohm. And SL, the inductive readiness will be 34 times of resistance. Okay, so which means if you ignore R and only use the SL inductive readiness for the entire line impedance, the error is only just 34th, about 3%. So if that's a big deal to you, you keep R. Otherwise, you can just ignore R for this transmission line. SC is the capacitive readiness between the conductor to the ground. So if the line is only 80 kilometers, so this value is about more than 3,000 times the resistance, which means about 100 times inductive readiness. So just think about, you have a line with a readiness, and the readiness to the ground, there's another readiness to the ground, which is 100 times more than the readiness in the ground. So the readiness to the ground can be ignored. So for this case, so this can be ignored, right? Whether this one can be ignored, really up to you. Whether you think 3% is a big deal now. But when the line becomes 250 kilometers, you see the capacitive readiness is only 300 times of R, only 10 times of inductive readiness. So this one need to stay for most of cases, because otherwise the error is too much. So what we're talking about is, so if this is like inductive readiness, there's a resistor, there could be some capacitance, right? So that transmission line can be roughly considered by this circuit. So this is R, this is XL, this is XC. Okay, for short line, for short line, and XC will be 100 times of XL. Okay, which means we can just ignore this IC, this shunt branch. But for long line, the IC is only about 10 times of SL. If you ignore IC, the error will introduce about 10% error. Okay, R here is only just 3% of SL. Okay, that's up to you if you want to consider this R or not. So if the conductor is has a very large size, very large radius, the very large value of GMR, you can even reduce R. So that's why for high voltage lines, usually R can be ignored for some cases. So the conclusion is, when the line becomes very long, we need to consider maybe all of them. At least we need to consider this capacitance. We cannot ignore this capacitance anymore. But for short line, we may be able to ignore this capacitance. All right, so let's move to line models. We'll take the same approach for all the 3 line models. First, we'll treat the transmission line as a linear bilateral 2-port network, which means the transmission line itself is just equipment. It connected to both sides of the system. So on left hand side, we call that the source voltage. On the right hand side, we call it the load voltage. And we assume current is coming from the left, coming out from the positive terminal. That's how we define the source, right? And the current is going to the positive terminal on the right hand side. That's why we treat the other side to be a load. But in reality, the line, this is just our assumption, but whether each side is a source or load really depends on calculation. If you remember how we use phasor diagram to determine the angle difference between the voltage and current phasor, then we can decide the signs for P and Q, right? So we have to draw P and Q in the complex plan to know this equipment is really a active source or reactive load, or active load or reactive source, right? So if we take this model, there will only be 4 parameters we need to model this transmission line, no matter it's a short line, medium line, or long line. So our goal is to have this transformation. So we just treat the line as a transformation from the load voltage and current to source voltage current. Similarly, we can also introduce the inverse transformation. So this ABCD will be a 4 entries of one 2x2 matrix. So the inverse will give you transformation to transform from a source voltage current to a load voltage and current. If this line has no source, okay, so when we draw this block, if the inside there's no source, so we will see this line is passive. So if the line is passive, if you calculate determinant for this matrix, which is for the 2x2 matrix, basically just AD minus BC. So this one will be always 1. Okay, so we'll verify this one for all the line models. We can also study the line efficiency. The line efficiency mainly depends on the loss of active power by the line. So if the line doesn't have any resistance, resistance include the series resistance, which is R, and also the shunt resistance to the ground. So the active power sent from the left will be exactly the same as power received from the right. So efficiency will be 100. So if the line has any resistance, the efficiency will be lower than 100%. So in this case, we can calculate the 3-phase complex power from the left. Then we calculate the 3-phase complex power received from the right by subtracting the loss of the line. And efficiency only consider P, it doesn't consider Q. So it's only just received active power divided by received active power divided by the active power from the source. Another thing we can calculate will be the voltage regulation, because here we can treat the source on the left hand side, if this is a source, together with the line as a source. Everything this box as a source. Then we can evaluate the voltage regulation. Voltage regulation just treat the source side and the transmission line as the equivalent source, and evaluate how easily the voltage on the low side can vary with the loading condition. Okay, so we know if VR is exactly 0, that's the ideal source. If VR is very large, positive number, which means the VR can change largely if you increase the current. Okay, it's possible in AC system VR may be higher than VS. That can happen. If that's the case, the VR can be negative. So based on the definition, VR will be the no load voltage of VR minus the full load voltage divided by full load voltage. Okay, so we will follow those steps for each line model. Any question? So let's start from a short line model. A short line model basically just impedance model. It's not different from any like circuit we have studied in section 203. So load side, we can assume there could be a load equipment consuming the complex power SR. So the line will have inductance L multiplied by J omega, which will give you the inductive readings per unit length. Then multiplied by the length of the line, so that will give you the total readings. So this one will give you the total readings. And R is set to resistance per unit length, multiplied by the length of line will give you the total resistance. So this will be a impedance to model the line, including the series resistance and inductance. We know the line may also have the shunt conductance admittance to the ground. So admittance will depend on C, okay? And also conductance just means the resistance to the ground. For short line, from the example we show, we can ignore those two, okay? So usually the shunt capacitance and conductance are ignored. We only just consider this simple impedance. Let's find out this transformation, A, B, C, D. All right, so based on Kirchhoff voltage law, Vs is simply just VR plus a voltage drop on this impedance. And this impedance carry the current IR. So which is simply just VR plus Z times IR. Because there's nothing between the line to the ground. So the source current will also be the load current. So immediately we get this transformation. It's very simple. It's just a diagonal, not diagonal, it's a triangular matrix with 2 ones on the diagonal element and just single Z. So there's basically this line only have a single parameter Z. That's total impedance of the line. The line is passive, right? Because you calculate the determinant is just one. Determinant of this this triangular matrix with only ones on the diagonal will be 1. The next one we study the voltage regulation. We treat the source together with this impedance as the source seen from the load side. So this circuit is basically same as the equivalent circuit of a generator. Equivalent generator, we have the EMF E connected with the signal's impedance. But for this case, it's just source voltage connected with the line impedance. So in this case, the VR no load, basically just the source voltage. Okay, VR full load, they basically just VR and divided by VR. So if the power factor is lagging and low, much smaller than 1, so the VR will be large. A large VR means not very good source. So if VR is higher than Vs, which means the voltage regulation can be negative. So those 3 phasor diagrams correspond to lagging power factor, unity power factor, and leading. So for leading power factor, you see the VR can be longer than Vs. So that can make a VR be less than 0. Okay. So that's it. That's a short line model. So next, we move to a medium line model. So here we focus on pi model. There's also other model like gamma model. Gamma model is just the one we just discussed. We use one example. So if we can treat transmission line as impedance with X, L, R, And maybe on one side we have a capacitance. So this will be called the gamma model. Yeah, but there's some drawback with this gamma model. It's not very symmetric because we assume the capacitance all connect directly with the source. That will introduce some error. So a better model will be a split the capacitance into two sides, two equal half. Okay, so this side will have a IC. So if you split a capacitive reading into two for the same total readings, so what the value? So it'll be half IC or double IC. It should be double, right? Is that double? Yes, should be double. Because IC is just defined as J omega C. So double IC means this one, so which is equal to J omega C divided by 2. So the total capacitance to the ground is C. You either just use the C to treat it as single capacitive readings you put on either on left or the right, but either one will introduce some error on the other side. Or you split into half. The total C will into the half. So use each one to calculate the readings, which will give you the double readings of original one. Then you give this one to each side. So this model is called the pi model because it's really the shape of the pi. All right. So in this case, we may need to model the total shunt admittance of the line. Why? Y is actually the admittance of line, which is the reciprocal of the impedance to the ground, which will include both real part, imaginary part. Imaginary part will be basically depending on the capacitance. The real part is just model how much the energy is lost to the air or to the ground. So usually the G can be ignored, but depend on the design of the line. If you are able to deal with realistic the line data, you may see some data they may or may not provide G, but usually C will be needed to model the system. G here is just related to the such as the corner effect. If this corner effect really a concern, that causes the loss of energy due to the leakage current over the insulator, you may want to model this G. So use the G to model how much energy is lost due to this effect. If that's not big concern to you, if you don't need to worry about that one, usually G can be ignored, but you still need to model C here. C is aligned to neutral capacitance per unit length. So if you calculate the total capacitance between two conductors, you need to divide this capacitance into half or multiple by 2. Which one? Do you remember? So if you calculate the total capacitance between two conductors, and now you want to know the capacitance to the ground or to the neutral point, that's a double or half. That's double, right? Yeah, that's a little bit. You can easily make a mistake. Let me give you the find that case for you. So if you calculate the capacitance between the two conductors, and the conductor of each one will be double the capacitance between the two conductors. Okay, so. All right. So to make the balance of the left and the right hand side of the transmission line, so we just split the total the shunt admittance of Y into half. And on each side we just treat it as a lumped model. Okay. So we'll have this pi model. So in this pi model, on the left hand side we have a source voltage. We have source voltage, source current, and low side we have low voltage, low current. So also there's a current, which is the line current, that is different from the source voltage or low voltage because there are two shunt branches. So we want to find out this transformation ABCD. First, we find the VS, the source voltage, equal to low voltage plus the voltage drop along the line using the line current. Source current is the load, the line current plus the current going to the first branch. The first branch is basically just VS multiplied by the conductance, admittance. Then from the Kirchhoff current law here, we know this line current is equal to low current plus the current going to this shunt branch. So we're able to get the first formula, then use to do some simplification. We'll have the equation for source voltage. And for the second equation, to calculate the source current, we'll plug into the formula for the line current, and also we plug in the formula to source voltage. So we'll get this one. So after some simplification, we have this one. Okay, so we use some colors to match the result to the transformation. So finally, we'll have this transformation. So compared to the short line, so this impedance stay, but all the other elements are different, right? So for the short line, this one is 0, right? Remember, because if you ignore this Y, so this one will be close to 0. And for the two diagonal elements, those two are new elements added to the diagonal. So if Y can be ignored, this one is also close to 0. All right. So if Y is very small, this model will go back to the short line model. Will become 1, 1, 0, Z. Okay, next the line is passive because if you calculate the determinant, you calculate this orange item multiplied by green item minus B times C. So you can easily prove that's 1. So only this 1 is left. All the other elements involving Z and Y will be canceled. So the line is passive. Okay. Yeah, I stop here. So we'll continue on Wednesday. On Wednesday morning, please do a quiz for the previous session, the line parameter session.